Welcome to the hidden variables, and today we are going to solve an electrostatic problem using the methods of images. Consider a ground conducting sphere with radius capital R which placed midway in between two identical point charges separated by a distance 2d. We would like to find an exact expression that relates capital R to d in which the total force exerted on each point charge is 0, and then evaluate when R is much smaller than d. Conceptually, we can see that the 2 point charges are going to generate an electric field that's going to cause charges to be drawn onto the surface of the conducting sphere in order to cancel the total electric field inside the cavity of the sphere. Because we are interested in the electric potential outside the sphere, we can place an imaginary charge inside the sphere in order to guarantee zero potential on the boundary of the sphere. By doing so, we can neglect the surface charge distribution and simply consider the 2 point charges. Before we get started, we must consider two important aspects: the superposition principle of the electric potential and the symmetry in the problem. We can see that by those two aspects we can solve for the right hand side charge and then extend our solution to the left hand side by adding up those two potentials. Using the symmetry of the problem, we place a charge q prime at a distance small r from the origin. We define the angle theta from the axis to the radius, and we would like to know that the potential cancels along the surface of the sphere. To find the distance between each point charge and the surface of the sphere, we refer to our preschool trigonometric knowledge and see that the laws of cosine can become very useful. We write in red the distance between each point charge and the surface of the sphere. Writing down the electric potential from the right hand side as a contribution of 2 point charges q and q prime has to guarantee zero along the boundary of the sphere. Note that for the left-hand side charge, we can use the cosine identity cosine pi minus theta equal negative cosine theta. Choosing two convenient angles for evaluation, one of them is theta equal pi over 2, we get the terms q squared parenthesis capital R squared plus R squared equal q prime squared parenthesis capital R squared plus d squared. For the other case, let us choose theta equal to 0, and then we get q squared parenthesis capital R minus small r squared plus q prime squared open parenthesis capital R minus d squared, where we have used the following relation. Subtracting the second equation by the first, we see that q squared 2 capital R r equal q prime squared 2 capital R d. That means q squared is equal to q prime squared d over r. Plugging in back the result into the top equation, we see that the q prime squared term cancels out, and if we move everything to the left hand side, multiply by small r, we get a quadratic equation dr squared minus r parenthesis capital R squared plus d squared close parenthesis plus d capital R squared is equal to 0. In order to solve that quadratic equation, we can simply leave everything in the parentheses and see that under the square root, the second term only going to flip the r squared plus d squared to r squared minus d squared. While taking this square root, you're going to have the following result. Note that the second result when r is equal to d does not applicable in our physical case because our point charge has to lie inside the sphere. Therefore, we can plug it back in and find that q prime is nothing but q r over d. Now that we have found our parameters r and q prime, we would like to construct the left-hand side's image charge. We notice that due to symmetry, the q prime of the left-hand side is going to be the same q r over d and is going to be placed at distance r from the origins, but now for the left. Using Coulomb's law, we would like to write the total force exerted on a point charge q at the most right-hand side. This is going to be a contribution of three different forces: the real charge on the leftmost side and the two imaginary charges lying inside the sphere. If we account for the distances, we can write the following. We equate the force equal to 0 and now embarks upon a series of algebraic operations. First of all, we multiply the entire equation by d squared. This will simplify the second and third terms. Now, what we can do, we can plug in q primes, which we know is r over d, and take as a common factor d squared q squared, equating that to 0, and then using a little bit of more algebra, we can simplify our equation by cross-multiplying. Moving everything to one side and equating to 0, we can further simplify and expand as much as possible to get an equation which relate r to d, and we have an 8th order relation between those two. This equation is quite difficult to handle by hand, and I'm not even sure it's possible. There are two options. First of all, use the information we are given and see that d is much greater than r. That means that all the higher order r will have a very little contribution and will yield a very small number. What we will do is keep only the first order of r, and therefore we have negative 8d to the 7th r plus d to the 8th equal to 0. Solving for r yields r equal to d over 8. The second option is to use the computer, and we can see that r is equal 0.124909d, and our result, r was 1/8, which is 0.125. As you can see, those are in great agreement with one another. Thank you so much for watching and sticking up to the end. If you would like to see more content, let me know in the comments below what would you like to see, and feel free to give us a like and subscribe to the channel. Until next time, goodbye.